So we start from recap of last lesson, which was about proteins. So proteins are molecules. They have a primary sequence, which is encoded in letters. They are made of 20 types of amino acids, which are also grouped in classes, which is very important because these classes share biochemical properties. And this is relevant because, as we see, the protein fold in a specific three-dimensional structure, which is very much related to the function that the protein is going to have in the cell. And this structure is basically, let's say, it's encoded in the sequence itself. And we've seen that basically there is this homology concept. So proteins can accumulate mutations throughout evolution, but they would keep folding in the same structure, even though they accumulated some mutations, if they keep performing the same function. So function wants to be preserved, and this is very nice because in the end, the amino acid classes I was telling you about are really relevant for this, in the sense that, of course, you can have mutations between amino acids that share the same biochemical properties, and so you can see different sequences that will fall in the same structure. And these sequences are called, this group of sequences are called protein families. You have seen yesterday in the exercise the examples of these protein families. The sequences in a protein family can be aligned through what is called multiple sequence alignment. And this multiple sequence alignment is a nice object because it allows you to get some statistics out of it and, for example, measure this very important effect, that is coevolution. Covariation, coevolution, we've seen that when a protein, in a protein structure, you have contacts between amino acids. So amino acids in contacts are interacting, and these contacts are basically, they can undergo also mutations, but this mutation needs to be compensatory in order for the contacts to be maintained. And you really see this effect in the alignments, and this is very useful. We've seen some classical metrics to measure this effect through mutual information. And this is a course about machine learning, so why was this important? We will see it when we will get to protein language models. So large deep learning models that learn from all the sequences that exist in the databases basically learn this effect. And that's why they're so good in predicting protein structures, just from sequence data. So I think that was relevant. And we've seen examples of contact predictions yesterday. So now we change a little bit the flavor and we move to machine learning. And in the end, you'll see what deep learning is. It's just a modification of machine learning, basically. And did you move it? I didn't move it. Okay. I'm independent. No, right, but you're right. This is the right slide. So machine learning in general. So sorry, because this is going to be very, let's say, general. I will try. So we'll move apart from proteins a little bit. I will try to give you some examples of very basic and important models that are very useful to understand what will come later. And I will try to give you practical examples that are related to proteins. So stay with me, because next lesson is going to be protein language models. So if we are kind of on the same page with this lesson, we'll get the next one better, and we'll go back to protein, I promise. So what is machine learning? How many of you know more or less or had to do in their life with machine learning problems? None of you? Oh, okay. Some of you know what we're talking about a little bit. So machine learning means that we want to create a mathematical model, set of rules, basically, that allows to, given an input, on which the model is, we say, trained, it's able then to generalize and make accurate prediction on data that the machine has not seen during the training. So we let the machine learn on some data, and then we want to make prediction on an independent set that the machine knows in principle nothing about. It's kind of like magic in this sense. So the data. As I said, there is a training set that it's typically larger than the test set, on which the machine learns basically how to fit the input and make a prediction. And then we have a test set. This has to be really independent from the training set. So you should really make sure that you don't have data that were in your training set. Why? Because then you're gonna, at some point, ask yourself how well your model is performing these predictions. And you need, it's like cheating when you do it on data that has been seen in the training, because the machine has already learned how to fit those data. So this is a very important point. And we have, let's say, two main strategies, two main types of models. One, let's say, it's probably more understandable if some has never heard of machine learning before, which is supervised models. It means that you have a ground truth when you train. So it means that you want to predict some properties that you know something about. So basically on your training set, you know the properties that you want to predict, and you pass it to the model. So the model will check, will make some prediction and check on the true label, where label here means basically the properties you want to predict. So you have a training set, data points in your training set. Each data point has associated a label, which can be, I don't know, hydrophobicity, for example. Okay? And then you want to predict that label. Of course, on your test set, when you want to evaluate your model, you also know the labels so that you know how well the prediction is going. But you don't tell anything to the model about the labels. You just let it predict. So you train it on this information. But then, of course, in the prediction, this will be a blind prediction of this property. Okay? In an unsupervised learning framework, and by the way, protein language models are unsupervised models, so we'll get there, you don't have any external labels. So basically, the machine will learn internal patterns that are inherent to the data, which is, let's say, probably less intuitive to grasp, but I think it's very cool. Because it learns statistics of your data, it learns the distribution of your data just by looking at the data. And it's able to still make prediction. Okay? For now, of course, when we start talking about machine learning, we will focus on supervised approach. So during the training, we know what we want to predict. Okay? But this, I hope, is going to be clearer in the following. So now some like key concept that will apply for every model: supervised, unsupervised, machine, deep learning. These are very key concepts. This is the loss function concept. So this, okay, it moved by itself, sorry. So basically in machine learning, you input the data to some model, let the model make some operations on your data. And then in the end, you ask the model to make your prediction, to make a guess. And at the beginning, your guess, the model guess, will be completely wrong. So we say that the model learns by making mistakes. So the loss function quantifies mistakes. So how wrong you were in your prediction. So, for example, I told you about the labels. The labels are usually indicated with letter Y, while the input is indicated with letter X. And so you have some notion of the truth, of your ground truth during the training, and you make, that's Y true, and you make some prediction Y correct. So basically, the difference between the two is the error that you are making in your prediction. So this is the loss. And what is training? Training is exactly trying to minimize this loss. So it's an optimization problem. You have to fit your data in some way to your model, make your prediction, check the loss. The loss is high, bad. We go back and change the parameters of our model in such a way that this will be minimized, so that we will be less wrong the next time. So in each epoch, you see this plot. This is the training loss, because you can calculate it, of course, on the training and on the test. And on the x-axis, you have epochs. What are epochs? Epochs basically is the number of times that you run the model. So you let the model do its operations once, calculate the loss, then go back, change the parameters, because of course, when we let the model do its operation, we have some free parameters. It means that we combine our input in some ways, like weighting the features that are in our input with some parameters that are at the beginning completely unknown. That's what the model is learning. So when the input goes through the model, it will basically set this parameter at random at the beginning. Then it will check for the loss and change the parameters coherently with the loss. But we will see this in a second. This is to say that the loss has to be minimized during the training. And on there is here, let's say, you see on the test set that the loss at some point is actually, it's minimized at the beginning and then it's going up again. This is like sick behavior. We want to stop the training here. Why? Because we don't want to do overfitting. It means, overfitting means that you are changing your parameter at some point just to fit exactly the detail of your training set. So the model loses its capacity of generalizing to unseen data. It's just fitting the training set perfectly. From the training loss, you see it continues to go down, because of course it's doing better on the training data, better and better. But it's actually really adjusting the model for the training set. So lost generalization capacity. So there are some concepts that are introduced here that will be clear in a second. So this is just a sketchy example of a neural network. You have an input, you have some weights, some operation in which you want to combine your input, and then you have your prediction. So the forward pass is basically doing the operation, which typically are simple operations on your input, doing your operation and make your prediction. This is the forward pass. Then we've already kind of seen the concept of backward pass, because when you want to minimize the loss, it means basically that you want to go back, and that's where the model is learning. So at the beginning, you start with random weights. Then you make some mistake, which depend on the parameters that you have guessed, let's say. And then by minimizing the error, it means that we have a back propagation in the network. So basically, we go back by looking at the gradient of the loss and change the parameter coherently. So we want to minimize the loss, and we want to adjust the parameters in the model to make, let's say, a smaller mistake in the next forward pass, in the next epoch. Okay, so let's go a little bit more into this. So the loss gradient, what it is? Basically, the loss gradient is how much the loss changes when you change your parameters. Okay? So what you want is to change your parameters in the opposite direction of the gradient. You want to go back and minimize the loss. So what you do is you simply change the parameters, you take their old value and just change it a bit in the direction of the gradient. So what you need to do this is to calculate the gradient of the loss. So it's just a derivative of the loss with respect to your parameters. Okay? This is, just ask me questions on this. This is quite a complicated concept, I think. It's not that one digests it right away, I would say. You need to put some hands on it, I guess. But the concept is we make a prediction, we make a mistake, and this prediction, of course, it depends on our parameters, and we will see it through an easy example now. But of course, y is a combination of your input and your weights, right? So it depends on the parameter. So what you want is to, next time, make a smaller mistake, minimize the loss. And so you want to change your parameters in such a way that you are going in that direction of minimizing the loss. Questions? How unclear is this? How much unclear is this? Maybe with an example, it's going to be a little bit simpler to get this. So, okay, then this is a hyperparameter that you set. It's the learning rate. You see it here. I am sorry about the, so basically this is a picture I got from the web. It is new, no? So you move your parameters in the direction of the gradient of the loss of a step size that is your learning rate. And this you set it. And you will tune it in the sense that you will see that if your step here is too big, you're not going to learn anything. You'll see it from the loss. That's what the loss is, what you look at when you train. And if the loss is too high, it's not going down, it's oscillating, then the model is not actually learning, right? Because the error is not minimized. It's still going to make big mistakes. So by looking at the loss, you can kind of tune your learning rate and know how big is the step that you want to make. Okay, these are the key concepts here. Then you have some typical optimizers that are used. I'm not going to go into this because you can basically, you have libraries to do it, to do these minimizations. You don't do it by hands, lucky. So you have several ways. You can basically, one of the most famous is stochastic gradient descent. So you use random batches of data to calculate the gradient. But okay, this is technical, let's say. Let's go to an example that is going to be, maybe hopefully it will help clarify it. So linear regression is the easiest thing you can do in machine learning. So what you want is a linear fit of your input X to predict your label Y. Okay, so you want a linear combination of your input through some weights. The concept of weights will stay throughout the course because this is how neural networks make operations. So in this case, weights are maybe something that is familiar with you, to you, because this is just trying to fit your data with a straight line. So same problem as before. I took this picture from somewhere, so this is actually Okay, following the formula is the intercept of your line that you're trying to fit. And so also here, and this would be just one, no? The slope of the line that you're trying to fit. So what is the loss for this type of problem? This is a very simple loss. You make your linear combination, at the beginning it is completely guessed, and then you calculate how much you go far from your true label y. So y is your true label, y hat is your prediction, and this is what you want to minimize. Just the square of the distance between the two. Easy peasy. Okay? So you will learn a linear fit that gives you the y. So this is a regression problem. In machine learning, you have either regression problems or classification problems. Regression problems means that you want to predict a continuous values. That is y here. Okay? It's not binary. It's not that you want to predict 1 or 0, you want to predict y, which can be anything in the real number world. Okay. This is a simple example of regression. The simple example of classification, unfortunately, is called logistic regression. This is not my fault. I think this is really mean because, I mean, it's not a regression, it's a classification. So just, I want you to focus on the difference between regression and classification. I hope you got it. And now, unfortunately, this is a classification task, logistic regression. What is it? Simply what we just said. So what you do is still a linear combination of your input, but then you apply a sigmoid function. So you transform the linear combination that you got with a sigmoid, which is it has this functional form and it has this shape as a function. So what you're actually trying to do is to push your y either toward 0 or toward 1. Why? Because, because your labels now are not continuous values. What you want to predict is a binary value. So you want to classify something that is either 1 or 0. You need this trick. And of course, now the loss changes. So the loss here, it seems hard, but it's not. If you remember the entropy concept that I gave you in the first lesson, this entropy measures how uncertain you are about something. So it can be used as a loss, basically, to quantify the error. And the trick here is that if your y, so your true label that you're still using here, is 0, okay, we are in a binary classification, so your labels are either 1 or 0, right? If your label is 0, this part of the loss will be 0. So you will just focus on log of 1 minus y hat, which will be very high error when your guess is close to 1. It would be very low error when your guess is close to 0. And vice versa. If your true label is 1, this part of the loss is going to be 0, and you will be high error when you are close to 0 and low error when you're close to 1. Okay? So this simple classification model is very important and very effective, and it is used in combination with probability language models. That's why also I'm mentioning it, because I want to give you some, let's say, the idea and some common language for what we're going to use later, no? Okay, questions here. Is this kind of clear? So I think through this example, we see better some concepts that we've seen before. So it's It's just more practically clear, no? This is a loss in our case, and when we train, we go back changing the weights in order to minimize this loss. And we do some steps, some epochs of training, until we go to convergence. Convergence, we see it through the loss. When the loss is not going down anymore, the model is not able to learn. And that's okay. Of course, remember to check the test loss, because you could go into this overfitting regime, and you don't want that to happen. Good. Example. So back to proteins, just to be a little bit more comfortable. This is actually the exercise we're going to do today. So logistic regression. So it's a classification task, and your input, your data will be protein sequences. Okay. So what we did, we took from some databases some annotation of protein sequences regarding if they are folding their secondary structure as an alpha helix or as a beta sheet. There is a trick, biologically there is a trick here, because we focus on proteins that are either fully alpha helix secondary structure, fully beta sheet secondary structure, which it happens. We have proteins like that. Of course, we have many proteins that have a mixture of the two. Some beta sheets, some alpha helix. We just ruled out these proteins to make this exercise and to give you this example, okay? So in your dataset, you're going to have either proteins that are full alpha fold or full beta secondary structure. And we assign a label of 1 in one case and 0 in the other case. So this problem can be recast as a binary classification task. You agree? You have two classes. Every time you have two classes, you can formulate your problem as a binary classification task. What you do is you fit your input through your logistic regression, and basically, so applying the sigmoid to your linear combination. Of course, there is a trick that I didn't tell you. The sigmoid is a continuous function, so you have to set a threshold, which is usually, since the function is between 0 and 1, the typical threshold is 0.5. So if your value y is above 0.5, it means you're predicting a 1. If it's below, you're predicting a 0. Okay. So how many of you knows what is one-hot encoding? Did you ever hear of it? So what's the problem here when we want to input a protein sequence? Do you see some problem with that? So we want a mathematical model. In this case, we want to make a linear combination of our input features. Yes, that's it. So sequence are letters. How do we handle letters in this case? It's kind of hard, right? We need numbers. So one-hot encoding is the strategy to turn a letter into a number. So how does that work? Remember, we have 20 amino acids. So we have an A, for example, letter A, alanine. This is going to be projected, into a vector that is 0, 0, 0, 1 in just one position, 0, 0, 0. And this is in an alphabet that is 20 dimensional, no? So you have basically these are 20 elements, as much as your amino acids. Each amino acid is encoded by one position. So if you have that amino acids, in that position you will have a 1. All the rest is going to be 0. Is this clear? It's easy, no? In the end, it's kind of intuitive, this, but it's very much used. Anytime you have some data that is not directly processable by a machine. Okay? Now, oops. Okay. These are some ideas or evaluation metrics, because of course you are going to use it. So at some point your model will make some prediction. How good is this prediction? This is why we need the evaluation metrics, no? For classification, we have two main concepts. One is precision and one is recall. Recall can also be viewed as a sensitivity of your model. So the precision is you are making a prediction of a subset of your observations, and you calculate how much positive correct predictions you have on the predicted labels, which possibly are not the full observations in your dataset. So that's why the distinction. So above the prediction that we have, how much they are correct. Recall is like how much they are correct over all the observation. So suppose you make the prediction just on a subset of them, then you know how much you got correct over the whole observation, even over the one that you didn't predict. So it's sensitivity of your model. For classification, many times you use a combination of the two, which is their mean, basically. They have one score. This is important because sometimes you can have unbalanced classification sets, in the sense that you have, suppose you have a binary classification, you have a lot of zeros in your dataset and few ones. These metrics in this case can be kind of poisoned by this. Why? Because you have so many zeros. If you don't make a distinction between the classes, basically the model probably thinks that it's going to do, that it's done great because it got so many zeros correct. But actually, you are much interested into the ones. It's too easy to predict the zeros, right? Extreme case, I would predict all zeros. I would still have high accuracy if there is just 1% of my data that is 1. So that's why you need a combination of these two. For regression, we already seen something. For example, there is the mean absolute error, which is even easier than the mean square error. It's just without the square. So you take the difference of your prediction with the true label in absolute value. And then you have correlation metrics. So you can have Pearson correlation that tells you linearly the correlation between the prediction and ground truth. Spearman is not with the continuous y values, but with the rank. So it tells you how much the rank of your predictions, so the order that you predicted, is coherent with the order of the true label. Okay, this is just to, let's say, give you some metrics on how you can quantify the generalization power of your model on unseen data. Okay. Of course, this is done on a test set in which you have the ground truth, but you're not using it. So I hope this is clear. The true label, the ground truth label, are used during training. When do they come into play? The labels, the actual ground truth values that you want to predict. When do they come into play during training? Yes, in the loss. Okay. When you calculate the loss, you need your labels. You need the truth. On the test set, you make a blind prediction. Now I've trained my model. The weights are fixed. They are learned. Then I make a forward pass through the model with my test data. and see and check how the prediction is through this metric. So, of course, here to check how the prediction is, you need again the ground truth label, but just as a check. You are not using it. You are using what the model has learned on your training set. Okay? Good. Now we move a little bit into neural networks. So the difference is really small with what we just said. The difference is just that we add what we call a hidden layer to the model. Okay, so these are inspired by neurons, and in fact, yes, on the way the human brain works, I think you've seen it very well with Fernando. So basically, your hidden nodes will receive a linear combination from your input. It will combine your input with some weight, reach a node, and the node is going to fire, just to make a parallelism with the neurons, if the signal it received is above some threshold or not. So it will activate through a nonlinear function, depending on the input it's received by combining the input features. So this seems abstract, but I will show you that it's completely not. So the key point is that you have an input layer, a hidden layer, and an output layer. Okay. A simpler example of this is a multi-layer perceptron. You see here, I don't know if the word perceptrone came out in the neural network class, in the yes, in the brain framework, let's say. But basically, it comes from there, from the brain. So, what is it? What's it doing in the hidden layer? This is the operation this simple network is doing. So, as I told you, linear combination, you recognize it, no? It's just the one as before. You take a linear combination of your input, and then you apply the sigmoid function to activate. It's like saying, okay, my node which receives this linear combination will fire or not, depending on the sigmoid output. And then you redo the exact same thing. This is the hidden features. Okay? So here you actually have as input a linear combination of your x. Then you can call this x tilde, for example, and you take a linear combination of your x tilde again. And the sigmoid of it, again, same trick, apply a nonlinear activation, and this is your output. So it's just redoing that linear regression operation twice in this case, because we just have one hidden layer. Okay? Why is this useful? Because logistic regression being linear, it will try to fit your data to separate classes with a straight line. Okay? So this is a typical example in which this wouldn't work, because you have these interconnected, let's say, groups of data. When you try to separate them with, they're not linearly, clearly not linearly separate. Okay, so when you try to separate with a straight line, you're gonna make errors. What a MLP can do, it can learn a curved surface that separates them. This is a nonlinear operation, right? It's made up of linear operation, but it's not linear operation. So it can learn more complex patterns in your data. If you have nonlinear dependencies, which many times is the case, this is for sure the model to use. An example that resembles the one before is that, for example, you add to your input two new features that we use just because, for example, net charge of your sequence or net hydrophobicity of your sequence. These are for sure not linearly related to it. The relations are much more complex between being beta or alpha structures. So the prediction is the one as before. We want to still see whether your sequences are, whether the structure associated to your sequences are alpha, beta, or it's an alpha structure or beta structure. But the new features that we introduce are for sure not linearly related to these labels. So in this case, it's suggested to use, that's the key message from here. Okay. Question before we move to classroom. Is this okay? So, what is a deep learning model? It's simply we can take this model to play this trick many times, which means having many hidden layers. This is a deep learning model. Okay? So, nothing more than that. Of course, when you move to deep learning frameworks, you can have more complex operations and architectures. It doesn't have to be a linear combination of your features. This is typical of this particular model. You can play different kind of games. But the key message is that it's called deep learning because it has a lot of these hidden features, hidden layers. Okay, now we move to something a little bit different, which is still very useful, and it's clustering. I think you have heard of clustering at least once in your life because it's like useful many times in everyday life, I would say, when you do data analytics. So what is that? You want to group your data based on their similarities. Simply that. So it is unsupervised because you just look at your X data and how they relate to each other. You don't have labels. You just want to see if they would group or not together. Group is a synonym of cluster. So it's unsupervised, but this is kind of, let's say, tricky. Unsupervised in the sense that it doesn't have labels, but it needs something that is, how many clusters do you want? Many times it needs the information. So, of course, to know this, it's a bit tricky, no? In advance. You have to kind of try. There are ways to, like, fix the optimal number of clusters. But in the end, you have to fix it in advance when you do the cluster. So there are two main strategies. One is just distance based, so you literally measure the distance between your data points. And it works when you have, mainly when you have spherical clusters. So in your data space, they group in a spherical way and not in very strange ways. Then this is gonna work. Or you can have density-based clustering. So this relies on the concentration of your data. So if you have some areas of your data space that are more dense of points, so there are many points concentrated there, this is highly probable to make a cluster. If you have scattered points around, they wouldn't do. This can be applied on more irregular shapes. It does. Your data doesn't have to lay on a spherical clusters, but it's a little bit more tricky to tune. Usually they have more than one free parameters, and they're a little bit more complicated to use. So I will just give you an example, let's say the main example of a distance space cluster, which is Keynes. This is very much used. I would say that it's the most used distance space clustering method, so it's useful to know it as an example. And you see here why you need to know the number of clusters in advance, because in the initial step you have to set the number of clusters that you want, which is k. You start from random centroids. Centroids are literally the center of your clusters, but at the beginning you don't know. So the algorithm works with assigning them at random. Okay, so suppose we select a k of 3. We want 3 clusters. At the beginning, we extract from our data 3 points at random. This will be our centroids. And what you do is you check for all the other data, their distance with the centroids. So they will be assigned to a cluster if they are closer to their centroid with respect to how much they are closer to the others. So this is a formula to say that your I point, xi point, will be assigned to the cluster to which its centroid is more close to. Very simple. Okay, you do this, and then you play you have 3 clusters now, no? You assigned all your points, you have 3 clusters. You recalculate the centroids, because now the centroids are going to be different. At the beginning, they were chosen at random. Now you have 3 clusters. What is the centroids? It's the average value of the points, of the x points that fall in your cluster. Yeah, it's written here. Just that. You have a cluster, you take the average, that's the center. Makes sense, no? Okay, but these are going to be different from your initial centroids. So you simply replay this once again. You have these 3 centroids, you go to your dataset and start assigning points to your clusters based on the distance to the centroids. The assignment now is going to be different, almost for sure. No? Then, after you play this trick, you recalculate the centroids and you play this trick again. Okay? What is it trying to minimize? How much your data are packed in a cluster, are close to the centroids of your cluster with respect to the other ones. What makes it a cluster is this. It has to be, your data has to be closer to the center of your cluster that you're assigned to with respect to how much you are from the other ones. Okay.
Yeah, I see the loss function. What is the free parameter we want to minimize according to that? The assignments, the position of the center.
Yeah, in this case, we have no weights to learn. It's not a learning process. It's just you want to minimize this assignment, basically.
The assignment.
And in this case, what you want to know are the centers, not the mu. Okay.
Yes.
So what you are changing are these centers of each cluster. So this is what you're learning basically.
But at the same time, those are means.
Hmm?
Because it comes kind of before and after. Because
Yes, you do it I mean, you change it, you do it again, and so on.
So what you want to minimize is the closeness to the centers, how much packed they are. But yes, you don't have, you want to optimize the grouping, no? So how close they are with respect to the other groups, how close they are in one group with respect to how close they are with, from the others. But you don't have weights here, and in fact, it's not, we cannot say it's a training, it's an optimization.
Can I just ask something? Because I don't really can read, but I want to like to see over which x's are we summing up in the update and the loss function. Because we are updating in over all x or over the x are the cluster.
X are in the cluster.
X in the cluster.
Sorry. Maybe,
Yeah.
If you can zoom in, Natalia, but it's also blurry, so I don't know. You can see. So
Yeah, it is up there for the x of the hierarchy.
here you are inside your cluster. Okay. So in a cluster, you have a distance from its center, from the data point to the center. And you do this for all clusters.
Yeah. So when we actually update the center, we are actually not only updating the center, but we are also um, changing the x's that are in the cluster. Because
Yes.
we changed
Yes.
here.
So one step, you assign your data point, you calculate the centers. When you have the new centers, you will do this again. So you will reassign your data points. So you are changing, yes, the way you are assigning points to the closest centroids, basically. Okay, I think, so maybe, yeah, I have another model, so we can go through it because it's a few minutes to say, which is the autoencoder. It's the first example of unsupervised model. Why? Because what it does, it's made of it's made of an encoder, which is kind of like a model, any model. Suppose it is an MLP that processes your data through linear combination, sigmoid, linear combination. It can be any model, but now it's in MLP, so let's suppose it's an MLP. Then there is a bottleneck. So just a hidden layer that you fix the dimension of, that is smaller than the dimension of the other layer and of the dimension of the input. This, and then you have a decoder. What is the decoder trying to do? It's trying to reconstruct your input data. So in this sense, you don't have labels here. The goal is to reconstruct the input. So you just need the input as a target. Okay, so it's an example of self-supervision, which is still non-unsupervised, just because it doesn't need an external label. And this is useful because in this bottleneck, of course, this operation gives you some vectors, right, in the hidden layers. These vectors here are very, which we typically call zeta, are very informative. Because here the network is basically compressing all the information that you need to reconstruct the input in a smaller space. So it's trying to really condense the useful features that it needs to do so. So in this sense, this is used for, of course, for dimensionality reduction because it's a small layer, but for feature extraction. So an example of this can be, you have a protein family. There is this EFN protein family. These are proteins. It's a protein family that is a bit particular because, of course, it's a family. So the sequences, as we learned, are similar to each other. But there are some of them that bind calcium, and others that don't. So if we use an autoencoder to parse, to encode our sequences in the latent space, we can look at the vectors in the latent space, at the zeta vector. And what we will notice when we use these family sequences is that they cluster in two groups. And surprisingly enough, a group is calcium binding and another group is not. So basically, even though we can see it by eyes because the sequences are so close, this is useful to capture some features that are in the data that the model is capable to see. Probably, almost surely, because we went in high dimension before doing this compression. So we gave this combination of features that we are making a lot of flexibility. But then we compress and ask it to summarize what it has learned in the bottom. So the network is playing the game to reconstructing the sequence, the input sequences, but indirectly it learns these representations that are meaningful. We see that they're meaningful because they make sense. In this case, we know this binding calcium thing, and so we can check that they're making sense. Okay, just one thing that I forgot to say when I was on k-needs. This is very important. This me or U map, you will see them in the future also. It's just 2 dimensions. We have these vectors that live in very high dimension that are generated by the network that we call representations, that are the ones that are generated in the hidden layers, for example. And if we want a way to visualize what's going on, we need to reduce their dimensionality to have a 2D block such as this one. And so this is just a way to have a dimensionality reduction in 2 dimensions. It's very much used. You get this projection of your high dimensional data in 2D. And it's good because it preserves distances. It's not always perfect, of course, otherwise we wouldn't need to go in a dimension, but it's very useful. And yeah, one element is like going back to biological sequences. I know this was a little bit harsh, I'm sorry, but it's a little bit, let's say, far from biology apparently, but we can use it for biological sequences, for example, and they are used a lot. And there we have some sort of problems that we have to face, like the fact that this sequence space is so high dimensional, there are long range dependencies. And here, maybe what I wanted to point out is mainly these 2 points. So poor generalization and risk of data leakage. What is that? So homology we've seen is so powerful, so useful to understand stuff about protein structure, for example. So evolution tells us a lot of information. But in the case of machine learning, we need to be very careful because of homology. So I told you that now I hope you can appreciate better. If I have some data points that is in my training set and I use it to test, this is kind of cheating. The metrics, the evaluation metrics, precision, F1 score, whatever you want, is going to be higher than it should be, because it has already learned how to deal with that data. Okay, so one has to check that you don't have the same data points in the training of the test. But then you can have homologs in your test set. And this is still kind of cheating when you want a model that is able to generalize on any proteins. Suppose if you want to predict alpha and beta, then I want to do it on every protein. I don't want to work on, I don't want to bias toward a specific type of product. And possibly I want to see my performance, I want to check my performance in a transparent way, without inflating the performance. If I use an homologs, the model sees something very, very similar to what I see in the training set. So one has to be very, very careful also to rule out homology between training and test. Using the same or very similar data points for training and testing is called data leakage. And it's a very serious issue in machine learning. You'll see a lot of published papers with this problem. Well, nowadays you see a lot of published papers on AI, machine learning, and among them, there are some that says that their prediction accuracy, prediction capacity, generalization capacity is amazing, but then when you go and check very deeply, they are lying. Okay? That's why I wanted to point this out. And for me, this is all if you don't have any question. And I'll see you in the afternoon for the exercise. Yes?
Is there any specific reason why it's not working for biology? Or you're talking in general?
No. It is working for biology. I'm just saying that if we want to use it on biological sequences, we need to be careful about homology. Because it's not enough to check, okay, is X in my test set? No, okay, no, I also have to check, is X homologous to something that is in my training set? You really see this effect if you try to inject this. So very good performance with homologs in your test, then you start to remove it, and the performance is decreased. Because of course it's going to be hard to make a prediction on something that you have never seen before. This is kind of measure. And if it's not, it means you have a very, very good model, and that's great. But typically, it's expected that it will make some mistake. No? Okay? I think the exercise of the afternoon will help a bit to digest this concept. Also to see how they are actually used in practice. And we're going to do, as I said, logistic regression on protein sequences to predict whether they are alpha structured or beta structured. We have this label from the databases. We're going to use it for training, and then we're going to make a blind prediction on sequences and see how it goes.